All right. Yeah, and now for something completely different. Well, thank you. Thanks for putting this together. It's great to be here. I'm fully aware that I'm the last speaker before lunch, so I will try to keep things entertaining and brief. I've been working with AMReX for a while now, since 2017. Really, it's a fantastic project, and glad to be a part of it in some small way. I'll just point out that since over that time, we've really accumulated a lot of interested parties. We now have stakeholders from ONR, NSF, UCA, and AFRL who are all funding our effort on this. So, in addition, of course, to our original funding from Berkeley Lab through the ECP. So, with that, let's jump right into it. We're interested in solid mechanics, but particularly we're interested in problems that are kind of characterized by moving variable geometry. So I just have a kind of a random selection of interesting, relevant cases here, looking at like microstructure in energetic materials, looking at dendritic growth, so solidification in melted materials. Additive manufacturing is of course a relevant context as well. We're interested in damage of high explosives. We're interested in the deflagration of solid rocket motors. I mentioned that in the title of the talk. Rather than going deep into any one of these particular applications, I just want to sort of give a buckshot, little preview of all these different pieces, and maybe there'll be something that's interesting that we can talk about further. I think that phase field modeling is not something that's particularly common in this field, so forgive the experts in the area. Please forgive me if I'm giving you redundant information. But what I like this picture because the idea behind phase field modeling is we're going to take a system in non-thermodynamic equilibrium, and we're going to evolve it. And so it looks something like this. You have a free energy, and that free energy can contain chemical potential or surface tension or elastic strain energy, like any kind of energy that you want. Throw it all in there. Turn the crank and extract out this diffuse boundary governing equation called a phase field model. And so as you evolve your system, it might look something like this, where you start off in a high energy state, lots of interface, and then you evolve, you ski down to the bottom of the mountain, and you get to this low energy state. And a phase field is really cool because even though it produces this really interesting emergent behavior, a lot of the time it's actually relatively simple to implement. Not always, as I'll talk about in a little bit, but what I mean by simple is this is the governing equation for this equation, or this, what you see here. It's a reaction diffusion equation, first order in time, second order in space. That's the heat equation with a couple of nonlinear terms thrown in. So pretty easy, and actually really makes it a great candidate for AMReX. So my next slide, and this is the slide that I usually show to talk about, we use this thing called AMReX, and I need to explain all about that, and that's totally perfunctory here. Instead, I'll just say, why do we need AMR? We need AMR because phase field methods are historically very expensive because you need lots of resolution at these diffuse boundaries, and you don't need much resolution anywhere else. So as a matter of fact, in this community, almost everyone uses AMR, but no one uses AMReX except me. But we're really hoping to change that because it works fantastically for these phase field types of problems. So with that, let me go ahead and just start by talking a little bit about some of the material science applications that we're interested in. And this is work that has been going on for quite some time. I think I have a gallery image of a simulation that's something like this. We've really moved quite a bit beyond that capability. And this runs extremely fast now. It didn't used to run very fast before, but this is looking at evolution of individual grains in a heated up microstructure. So we're seeing coarsening of these grains and coagulation. Very, very powerful and robust framework for doing these kinds of simulations. But more recently, we've been looking at stuff like this: deformation twinning, hierarchical deformation twinning, and this is an example of the kinds of behavior that we're trying to look at, and we can actually capture it. Which no one, to my knowledge, this is not something that anyone else is able to do, and we can do this extremely quickly. And we're also interested in phenomena like this, where we see anisotropy-driven effects, so like faceting. If you're familiar with wolf shapes, probably not, but if you're familiar with wolf shapes or crystal growth, this is something that we can capture as well. Now, I mentioned dendrite growth. We're also really interested in dendrite growth, solidification. So this is something that we can do with AMReX and Alamo. Spinodal decomposition is another example. This one doesn't really belong in material science, but it's really, I think, freakishly cool. If you're not familiar with topology optimization, the idea is I have a domain and I want to fill it up with like 10% of material, and I want it to support a load here. Now give me the optimal arrangement of that material to support this load, and what do you know? It actually pops out a truss. And we didn't tell it to make a truss; it just pops it out, which is like mind blowing to me. And you know, again, you can maybe see here why AMR is so useful, because you don't know what your geometry is going to look like beforehand. So this is like the canonical case. That's a 3D case up there, and this has lots of applications in material science. I won't go into them here, but really powerful technique. Now, I said earlier, phase field, easy to implement. This is not always true. What I talked about before was a low order method, and there are other kinds of phase field methods that are very, very high order methods. Phase field crystal is a particular example where you actually try to model individual atoms using this technique. And the equation of interest is a Swift-Herrenberg type PDE, which, as you can see, is 6th order in space. So good luck trying to solve this using real space methods, unless you have an insane amount of computer time to blow with really, really tiny time steps. And the solution actually is to solve this in reciprocal space. And that was where we were really delighted to see the AMReX FFT capability, because now we can solve problems that look like this, which are high frequency in space, low frequency or low resolution in frequency domain, and get just really wild behaviors like this, where you can actually see, and if you're in the like atomistic community, you'll notice, there are like dislocations and there's grain boundaries, and you can simulate these atoms over very, very long periods of time rather than having to resolve individual atomic fluctuations, which is super cool. This also ran in a matter of seconds, which is really, really cool. We were super excited to get that working, and there are other examples as well, like some of the cases that I showed before are dramatically accelerated using this FFT capability. So I don't know exactly what else FFT is used for, but this is definitely one of the things that we appreciate it for. So, okay, just trying to make sure I don't take up too much time. I'd like to talk a little bit about some of our more solid mechanics-y applications, and here I'll delve a little bit into the AMReX development that we've done. So we are interested in solving equations that look like this, and if there are any mechanical engineers in the room, you'll recognize this as, this is the stress divergence equation. You use ANSYS to solve this kind of equation. And we said, well, we want to be able to solve these equations too using AMReX, but we really don't want to do finite elements. Finite elements doesn't make any sense at all on an AMReX grid. But an operator like this is also very difficult to do with something like MLMG. This is this elasticity tensor. It's a 3 by 3 by 3 by 3 tensor, which has 81 components. You usually reduce it down to like 2, but that's not something that MLMG was previously able to do. So that's one of the reasons why we really started working closely with the AMReX team, trying to work this in. And now we can use AMReX to do traditional solid mechanics problems. If you can do it in ANSYS or Abacus, you can do it in AMReX as well. I think, they were talking earlier about the reflux, and boy, did that take a lot of time to get this working, because calculating fluxes when you have tensorially fluxes of tensorial character, not fun at all. That it actually turns out that if you just use multiple ghost nodes, then you can eliminate the need to do reflex matching entirely. And yeah, it was pretty cool. And so we use this all the time. It's super fast, all the power of MLMG with geometric multigrid. and all the ability to do solid mechanics as well. We also look at, so we use diffuse boundary mechanics to capture interesting geometries. So we just sort of phase our modulus from finite to zero in order to capture the effect of like geometry related terms. So just an example of some of the stuff that we do with this. We are interested in doing relatively simple things like let's do tension tests with energetic materials, no problem. And we've lately been interested in dynamic impact loading of composite materials with damage evolution. You can kind of hard to see here, but you actually see some damage accumulating between these fibers. And then just as a mention, we have viscoplasticity and then finite strain elasticity. So it's fully hyperelastic as well, which really broadens the class of problems that we can work with. Now, a couple of us were talking about this before the session. If you do any kind of solid modeling, you know that really it all comes down to the constitutive model. So that 81 component tensor, that's a pain, right? And that's just the beginning. That's just assuming that you have like the best case scenario. It's just like linear elastic. If you're doing plasticity or viscoelasticity or pretty much anything else, all of a sudden you start accumulating all these other variables that you need to track. And so we developed what we call the model vector space, where we have a class of material models that automatically work on templated base fabs. So you can template your fab with these material models, and they come equipped with arithmetic operations so that they can be averaged and zeroed and multiplied by scalars as needed. The idea is that we want an Alamo, and we need an Alamo to be able to do the same kind of thing that you can do in a commercial software like Abacus, provide like a UMAT. I need to encapsulate my model into this piece of code without going and changing the entire structure of the software. And this gives us the capability to do that. Disclaimer, we are still working on GPU capability. So I can't guarantee that this is going to work on GPUs yet. Alas, most of our stakeholders are just interested in us getting it to run fast enough, not necessarily as fast as possible. So as much as that's an interest of ours, as long as we can get it to do what it needs to do, usually we stop there. So some more examples of this at work. This is phase field cohesive zone modeling. This is modeling fracture in an energetic material. We have some other fracture mechanics simulations over there. And in the interest of time, I'll keep moving along. We're also interested in using this technology to simulate rocket motors. So we get to say that, yes, as a matter of fact, we are doing rocket science. Although I don't think that the rocket science is anywhere as hard as a lot of the other things that you guys have talked about, like general relativity. That's definitely more complicated of a problem. I'm not going to spend any time on this slide at all. This is just to say, here's our model for phase field rocket motor simulations. If you're interested, I'd be happy to talk with you later about it. Something that's more interesting is this is the kind of thing that it can do. This is a representative element of a AP-HTPV solid rocket grain, and it is burning. So we're not resolving the fluid phase here at all. We're just looking at the evolution of the burn surface. So you can see this is why AMR is so useful. We only have to resolve that section there. We only have to resolve those interfaces. We're able to get dramatic speed up because of this. And a lot of people are always asking, can you do non-spherical particles? Because that's really important. Yes, we can do non-spherical particles, and we can even burn the Iowa State logo. And I always think I really should have done the University of Iowa logo, but I need to actually go rerun that one. So now I mentioned the solid, the elasticity aspect of this. This is something that's really a capability that we're really pleased to be able to do. This is a solid rocket motor that's burning and subjected to thermal flux and mechanical flux as well in the form of pressure, and we can actually resolve in real time the mechanical response, so the stresses and strains on our grain from these loads. And that's extremely important when you're looking at like fracture under deflagration or deflagration to detonation. All these problems are of very salient interest to like the DoD. Yeah, in interest of time, I'm not going to talk about this. The last thing I want to talk about is solid-fluid interactions. Even though we are a solids group, we're mostly interested in these solid mechanics problems. It is often inevitable that we need to be able to couple this to fluid flow as well. So over the past several years now, we have been working on a diffuse boundary method for coupled solid fluid flow. You might notice that this looks a little bit similar to like the immersed boundary method. And it is similar in that it is a diffuse boundary method. However, there is no parameterization of the method required. This depends only on the existence of something like a phase field order parameter, and the flow is entirely driven by the gradients of that order parameter. Once you have that, and I'm not going to go through all of these, but the idea is that you impose your boundary conditions through a mass, momentum, and energy flux. You can mix and match to get the kinds of boundary conditions that you need, and you can show that it converges exactly to the sharp interface solution. So the remainder, the last couple of slides, will just be examples of this at work. So this is an example here of a problem that's really hard to do if you have to track your solid fluid interface explicitly, but easy to do using this method. We can also do fun things like shock capturing or viscous flow past a cylinder, and moving to more like meaty challenges. If we want to solve these dendrite growth equations in the context of non-trivial flow, we can do this as well. So you can see there's a pressure drop that drives the flow across this growing dendrite, and now we're able to see the interaction of this complex flow field. And again, just a real, what's really exciting about the AMReX framework is that we have the ability to communicate the information back and forth from one module to another so easily because of the uniform box grid, or the uniform grid on which all these simulations occur. And the last one that I'll show is this forced flow through a eroding porous medium. So we start off with a semi-porous solid, and then the solid, which is that blue region, is eroded according to Alencon kinetics, or a phase field model. So we just throw in a phase field model to represent the erosion of the solid. And then at the same time, we solve the Navier-Stokes equations driven by a pressure drop from one side to the other. And so you see it equilibrates, and there's high pressure on one side, low pressure on the other. And then as you watch, you see as the solid starts to break apart, we see the fluid shooting through and then eventually reaching equilibration. This is really just sort of a fun example. We don't really have a lot of validation data for this, but it's fun for purposes of showing what the method can do. So with that, I'm going to not talk about these two slides. Instead, I will just acknowledge this is my group. It's really just me and my research group working on Alamo right now, but a lot of students have contributed. I have a number of collaborators. I can't list them all here. And just big shout out to the AMReX team. Always just a pleasure to work with them. They're extremely supportive, and looking forward to working with them in the future. With that, I will thank you very much for your attention and happy to take questions. Yes.
Yeah, so I guess you're doing everything with these boundaries.
Yes.
You're doing everything with finite difference-based approaches.
Yes.
That's awesome. But do you have any stakeholders or anybody who's interested in your work who's like, we really need an explicit boundary representation, for example, in the topology optimization example, and then does AMReX provide you any capability to do that sort of thing?
You mean like EB, like embedded boundaries, or?
Just everything that you're doing with like a diffuse representation of whether it's a cracked surface or an internal boundary in the mesh for the top-up example or whatever.
So because so much of what we're doing is phase field, we're pretty deeply rooted in this idea of diffuse boundary mechanics. I will say just the advantages of diffuse boundary methods are not strictly computational, but they're scientific as well. It's just very easy to formulate kind of arbitrary physics in that context. Certainly not close to the idea of moving to other types of boundary representation, but so far it seems to do the job.
There are other people who have done fun trackers with AMReX.
Yep.
My name is Akash.
What about metal casting? Are you looking at that problem?
No. There's no reason why we wouldn't. It just isn't one of our priorities right now. But we could.
Well, I'm saying that because I have been developing metal casting simulations using AMReX,
Mhm.
but what we're missing is how once the metal, when there is, we can model entrainment of metal oxide into the solid, but when the solidification happens, you start seeing metal oxide cracks,
Mhm.
and that's the capability we don't have.
Yeah.
Looks like you have that capability.
I mean, in principle, yes. And in reality, of course, that domain is going to come with its own kinds of challenges. But yeah, I think this could be maybe the tool for the job. Please.
Excellent talk.
Thanks.
And the question I had is, so which of these simulations were done with the FFT capability?
Just the one. Just the. Let's see. Where? Yeah, with all the atoms. I think it was just these. You can do others. We just don't really need to. But
What is the fundamental difference from this and the other simulations that you performed?
yeah, well, I would say, I mean, if you want to do this with kind of by, if you look at this, there's absolutely no reason to use AMR on this simulation, right? You would instantly refine everywhere. So it's really kind of pointless to do AMR in a simulation like this. And so it's kind of like if your simulation doesn't really require AMR, then it's probably one that would do really well with an FFT-based solution, and vice versa. Oh.
You thought about what you would do if you wanted to do AMR for something like that? I realize there's no, it doesn't make any sense.
Yeah.
But it's an interesting mathematical question, how you would synchronize it.
Yeah, so what I would really be interested in doing like this, and this is, we can talk more about it, is doing multi-scale methods where we have like this kind of simulation occurring on the smallest patch, and then like continuum on the larger patch. And in order to do that, of course, we need to be able to do multi-scale FFT. And yeah, I mean, I'd love to. This is more just like something we do for fun. We don't have much in terms of stakeholders in this particular application. But yeah, I think there's a lot of potential.
Really cool talk. The editor manufacturing example that you mentioned, do you also solve for fluid in there?
Not yet. That's the SFI that I was talking about towards the end. So, I mean, kind of like the dendritic growth is kind of in the ballpark. Additive manufacturing is again not one of our main focuses. We're mostly interested in the solids and the like damage. But yeah, absolutely, it's it's in the domain of things that we're looking at. Thanks. All right. Thanks.